in previous class we had discussed about the requirements for biasing circuits. Requirements for biasing circuits. Okay. What are the requirements for any biasing circuits? We have seen. What are the main requirements? Is that the biasing circuit, first it should fix the operating point in such a way that Q point should lie in the middle of the active region. Okay, so this is the first requirement. Then second requirement was that the operating point, it should not vary with the variation of temperature. Then third point, it is with the change in the transistor, the operating point, it should not change. Means with the change of the transistor of the same family, the operating point, it should not change. So these are the three basic requirements of any biasing circuit. Okay. So while we are using biasing circuit is generally used for fixing the operating point, and this operating point, if suppose this is fixed, okay, before the application of the input signal, okay, then after the application of the input signal, it should also lie in the active region. This operating point, it should not go to the saturation region, or it should not go to the cutoff region. Okay, this is achieved by using the biasing circuit. So the main aim of biasing circuit is that to fix the operating point in the middle of the active region. This operating point, it should not go to the cutoff region, it should not go to the saturation region, even at the extreme values of the inputs. Okay, and the operating point, it should not vary with the variation in temperature. And third is, if the operating point, it should be independent of the transistor parameters, because if suppose if any transistor, if it is faulty, then if we are replacing the faulty transistor with the new transistor of the same family, then IC, that is IC and VCE, it should not change. Okay, so these are the three basic requirements of any biasing circuit. So in biasing circuit, first we will study about fixed bias circuit. So the circuit diagram for fixed bias circuit, it looks like this. This is RC, this is RB, and this is VCC. This is operating voltage, DC bias voltage. This is DC bias voltage. Okay. RB is the series resistor. Okay. And across RC, we are taking the V out. Okay. So this is the circuit diagram of fixed bias circuit. Okay. Now, how we can get the operating point, that is IC and VCE. These are the operating points. Okay. So for this bias circuit, how we can determine the operating point? So this is emitter terminal, this is base terminal, and this is collector terminal. Okay. Now we will say in this loop, if we are applying Kirchhoff's voltage law in this loop, suppose VCC like this in this loop. So applying Kirchhoff's voltage law, it will be VCC, it is equal to, this is IB, and IC, direction of IC, and this is the direction of IE. Okay. So VCC, it is equal to IB RB plus VBE This is VBE. VBE. Okay, and see, in forward bias condition, VBE, it is equal to 0.7 volt if this transistor is made up of silicon, and this is equal to 0.3 volt if this transistor is made up of germanium, for germanium and for silicon based transistor. And this transistor, this junction, base emitter junction, if it is in forward bias condition, and we are seeing in this figure base emitter junction, it is in forward bias condition. Okay, so from this value we can determine the value of, from this equation we can determine the value of IB. It is equal to VCC minus VBE divided by RB. Okay, so we can determine the value of IB. From IB we can determine IC. IC, it is equal to beta times IB. So we can determine the value of IC, first operating point. Then we will see this loop VCC, RC, like this. So if we are applying Kirchhoff's voltage law for the output section, then it will be VCC, it is equal to ICRC plus VCE. This is VCE. Okay, so from this we are getting VCE, it is equal to VCC minus ICRC. This is second operating point. First operating point we have determined like this: IC, it is equal to beta IB. Second operating point VCE, it is equal to VCC minus ICRC. Okay, so this is about fixed bias circuit. So in case of fixed bias circuit, IC, it is equal to beta times IB, where IB is equal to, what is the value of IB? It is equal to VCC minus VBE divided by RB. Okay, and another operating point, it is equal to VCC minus ICRC. So these are the two operating points in fixed bias circuit. Okay, then we can determine the stability. S is equal to stability factor. Okay, so it is del IC divided by del ICDO. It is equal to 1 plus beta divided by 1 minus beta into del IB by del IC. Okay, del IB by del IC. So S, it is equal to 1 plus beta divided by 1 minus beta into del IB by del IC. So this is the expression for stability factor. So in case of fixed bias, in fixed bias circuit, how to calculate the stability factor? Okay, so how we can calculate del IB by del IC in case of fixed bias circuit. In case of fixed bias circuit, the expression for IB in case of fixed bias circuit, the expression for IB, it is equal to VCC minus VBE divided by RB, and it is independent of IC. The expression of IB, in this expression we are saying that VCC is fixed, VBE and it is RB. Okay, so it is independent of IC. So del IB divided by del IC, it is equal to 0 because all are fixed here. Okay, and it is with respect to change in IC, this expression it is equal to 0. So the stability factor in case of fixed bias circuit, the stability factor as it is equal to 1 plus beta divided by 1 minus beta multiplied with 0. So it is equal to 1 plus beta. Okay, and this beta, the value of beta is very high. This is the current amplification factor in case of common emitter configuration. So beta, the value of beta is very high. So as it is equal to 1 plus beta, and the range of beta it is approximately from 20 to 500. Okay, so the stability factor in case of fixed bias circuit it is very high. So if the stability factor is very high, then the stability of operating point, it is very low. Higher will be the stability factor, lower will be the stabilization of the operating point. Okay, so here we are saying that the operating point, its stabilization, it is very low because the stability factor it is very high. So advantage of fixed bias circuit is that the circuit is very simple. The circuit is very simple. Okay, and second one is only we are using RB, that is the base resistor. Okay, but the main disadvantage is that the stability factor S is equal to beta plus 1. The stability factor of fixed bias circuit is very high because beta, the value of beta is very high. So if say beta it is equal to 100, then stability factor it is equal to 101, which is very high. Okay, in normal case stability factor it should be below 25 for faithful amplification. Okay, so in fixed bias circuit we are saying that the stability factor is very high. So this is the main disadvantage of fixed bias circuit. Okay, then we will see numeric examples based on fixed bias circuit. Now we will see the load line analysis of fixed bias circuit. Okay, so load line analysis, it is the graph between IC versus VCE. So how we can determine the load line for this circuit? The circuit is, this is RC and this is RB, this is VCC and this is ground. Okay, how we can determine the load line? So we have to determine these 2 points. These 2 points are, this is VCC and this is VCC by RC. Okay, so this point it is equal to VCC by RC, this point it is equal to VCC, and then we are connecting this 2 point. So this is load line. Okay, so equation for load line, it is equal to VCC, it is equal to ICRC plus VCE. This is the equation, output equation. Okay, so we have to determine IC and VCE. Okay, how we can determine IC and VCE? Okay, so for determining IC, VCE it is equal to 0. Okay, so at this point VCE it is equal to 0. So IC it is equal to VCC by RC, and in this line the value of IC it is equal to 0. So we can determine VCE it is equal to VCC. Okay, so in this way we can draw the load line for fixed bias circuit. Okay, then we can also draw the output characteristics. Suppose this is IB1, IB2, IB3, IB4, and this is IB5. Okay, so suppose we have chosen this Q point. Okay, so how we can choose the Q point? By choosing the value of IB. How we can choose this value IB? Okay, by IB it is equal to VCC minus VBE divided by RB. So by varying RB we can fix the value of IB. So if IB is fixed, then we can fix the value of Q, operating point Q. Then after fixing this, if we are giving the AC input signal, then this Q point it should not go to the cutoff region, not go to the saturation region. So this is saturation region and this is cutoff region. This is for IB it is equal to 0 microampere. This is cutoff region and this is saturation region and this is active region. Okay, so this is the load line analysis for fixed bias circuit. Okay, now in this we are saying in saturation region IC saturation it is equal to VCC by RC, and VCE in saturation it is equal to 0. This is the condition. IC in saturation region it is VCC by RC, and VCE in saturation it is equal to 0. Okay, and IC in cutoff region it is equal to 0 here, and VCE in cutoff it is equal to VCC. We are saying here it is equal to VCC, and in active region IC it is equal to beta IB plus ICEO, or it is equal to beta IB plus beta plus 1 into ICBO. Okay, this is the expression for IC, and we can determine VCE. How we can determine VCE? VCE from the output expression. Okay, so VCE it is equal to VCC minus ICRC. So this is for active region, this is for saturation region, and this is for cutoff region. This is for saturation region. Expression for ICVCE, because these are the two operating points. Operating point, this is operating point, and this is again operating point. Operating point in case of active region, operating point in case of saturation region, operating point in case of cutoff region. Okay. For faithful amplification, this Q point, it should not go to the cutoff region or it should not go to the saturation region even at the extreme values of the input. If this operating point, if it goes to the cutoff region or to the saturation region, then the amplification will not be faithful. Okay. So if this is going, suppose in the cutoff region, then what will happen? Some of the negative half it will be clipped. If it is going to the saturation region, then some of the positive half of the input signal it may be clipped. Okay. So suppose the signal is like this. Okay. Now if Q point, if it goes to saturation region, then some of the positive half it will not be amplified. If this point Q point, if it goes in the cutoff region, then some of the negative half it may not be amplified. So the amplification it will not be faithful. Okay. So this is all about load line analysis of fixed bias circuit. Now we will see an example based on fixed bias circuit or base resistor circuit. This is biasing circuit, base resistor biasing circuit or fixed bias circuit. Okay. So in this figure we are seeing that RB it is given, it is equal to 530 kilo ohm, and RC it is given as 2 kilo ohm, and VCC is 6 volt. Beta of this transistor it is equal to 100, and this is in common emitter mode. Okay. And this transistor is made up of silicon. This is silicon based BJT transistor. So first of all, what we have to find? We have to find the DC load line. So what is DC load line? How we can determine the DC load line? So first of all, we have to plot VCE versus IC. Okay. This point it is VCC, and this point it is VCC by RC. So this point we have to determine, this point we have to determine, then we have to join these 2 points. Okay. So in this way we can determine the DC load line. Okay. So how we can determine this equation for DC load line? VCC it is equal to ICRC plus VCE. This is collector and this is emitter terminal. VCC it is equal to ICRC plus VCE. Okay. This equation. Now if VCE is equal to 0, okay, then IC it is equal to VCC by RC. In this axis VCE is equal to 0. Okay. So if VCE is equal to 0, then value of IC it is equal to VCC by RC. So this point can be determined by using this equation. Now if IC is equal to 0, then VCE it is equal to VCC. So in this way this point it is equal to it is equal to VCC. Now we have to join these 2 points. Okay, so this point is VCC. We can write here 6 volt, and this point it is equal to VCC by RC. So VCC by RC, it is equal to 6 volt divided by RC, it is 2 kilo ohm. So it is equal to 3 milliampere. Okay, and this is the axis of IC. So in this way we can plot the DC load line. So A part is over. Draw the DC load line. This is DC load line. Now we can join this. So this is DC load line. Now second, determine the operating point. So how we can determine the operating point? Okay. We can write VCC, it is equal to IB RB plus VBE. VCC, it is equal to IB RB plus, this is base terminal and this is emitter terminal, plus VBE. Okay, so from this we can determine the value of IB. It is equal to VCC minus VBE divided by RB. Okay, so in this way we can determine the value of IB, this IB, current IB. Okay, now IB, it is equal to how much? VCC is 6 volt, VBE, since the transistor is made up of silicon, so it is equal to 0.7 volt, and this is in these 2 junctions, base emitter lobe, it is forward biased, that is why it is 0.7 volt divided by RB is 530 kilo ohm. Here IB, it is equal to 5.3 volt divided by 530 kilo ohm. It is equal to 10 microampere. Okay. Now IB is 10 microampere. So IC it is equal to beta times IB. So it is equal to, beta is given as 100 into 10 microampere. So it is equal to 1 milliampere. Okay. So we have determined the value of IC, it is equal to 1 milliampere. Now this is one operating point. The second operating point is VCE. How we can determine VCE? Here IC it is equal to 1 milliampere. Okay, and we have to determine VCE. So how we can determine VCE? We can write VCC, it is equal to IC RC plus VCE. So from this equation we can write, this is VCE, VCC it is equal to IC RC plus VCE. So it is equal to VCC minus IC RC. It is equal to 6 volt minus IC, it is 1 milliampere multiplied with RC, it is equal to 2 kilo ohm. So it is equal to 4 volt. Okay. So the operating point, it is VCC, it is VCC by RC, and the operating point, it is 1 milliampere, and this is 4 volt. This is VCE versus IC. So these are the operating points. 1 milliampere is IC and VCE is 4 volt. Okay, so VCE and IC it is equal to 1 milliampere. So these are the operating points. So in this way we have determined the operating point of this transistor. Okay, then third is what is the stability factor. Now this is fixed bias circuit or base resistor circuit equation. How we can determine VCE it is equal to VC minus VCE. Okay, so VC it is equal to VCE, and so in this way we can determine VC. Then VBC it is equal to VB with respect to ground minus VC with respect to ground. So in this way we can determine these quantities, and this is fixed bias. This is fixed bias circuit. Okay. So we have seen few examples on fixed bias circuit. Okay, thank you.